Here's a little story about why limits in 3 dimensions are so much more fun than they are in 2. At the top of the page is the 2-dimensional coordinate system, x and y axes, and a sample function making its way through the coordinate system. And suppose we have a target point, x equals a, and we are asking what is the limit of that function, f of x, as x approaches a. From Calc 1, you should remember that there are 2 component limits to this problem because we can approach x equals a from 2 directions. The x-axis represents the domain, the set of all values that we are allowed to plug into this function, and a is our target point, and within this domain we can approach a from 2 different directions. We can approach from the right, and as we're approaching x equals a from the right, we are kind of following the function from that direction. And we can also approach x equals a from the left, in which case we are sort of following the function from that direction. And in order for the limit of this function at this point to exist, the value that it looks like we're aiming for from both the left and the right directions has to be the same. The limit of this function as x approaches a is defined to be the common value shared by the limit from the left and the limit from the right. Okay, that was Calc 1 with single variable functions. Now let's think about Calc 3, where we're dealing with multivariable functions, and the next upgrade from the 2-dimensional coordinate system is the 3-dimensional coordinate system. Now, one difference between Calc 1 and Calc 3 is that in this scenario, we are dealing with functions that depend on both x and y. The domain of this function is sum to all of the entire xy plane. The functions that we're tinkering with graphically are surfaces. I'm going to do my best. See how this goes. Okay, so here is a sort of a representative surface. I'm trying to indicate that, it's got the whole, there we go. There's a surface. Now, we can ask for limits in this context, just like above. We're about to ask for a limit. Limit of what? Well, a limit of the function. Well, when? Well, up here, I'll use the limit notation now. X was approaching a target value of a. So x representing values from the domain is zooming in on a target value. Let's take that down here. We need an entry from the domain to be zooming in on a target value for this limit. Remember that the domain is the entire xy plane, and so we need x and y to be zooming in on some target value. In other words, maybe there's the point AB, and we need our input variables, x and y, to be both closing in on that particular point. So x is closing in on A, simultaneously y is closing in on B. Now up here, we could only approach the target value A from the right, from the left. 2 directions. How many different ways are there to approach the point AB within this domain? Well, we could approach it from the right, I suppose. We could approach it from the left, I suppose. But we could also be approaching it from this direction. We could also be approaching it from this direction. We could also be approaching it from this direction, or from this direction. And even better, these directions of approach do not have to be straight lines. I can ride into this point from, say, the right on this straight line. I could ride into that point on that arced line, or that arced curve in the xy plane. I could swoop in on it from below by following that curve. All these different paths of approach to the point AB. And so for this to happen, there's not just two paths of approach, there are an infinite number of paths of approach. Now, if I take this target point up to, say, here, on the surface, what I'm looking at on the surface here is, let's say I'm approaching the point AB from the right, then maybe up here on the surface, I'm kind of riding in through those corresponding values. Or I'm coming in from the left on that straight line to AB, maybe I'm riding in on corresponding values from there, right? That would be the slice of the surface right above that path of approach. In order for this limit to exist, we need to get the same limit value from every possible direction of approach. But we cannot check the infinitely many results from infinitely many paths of approach like we can up here when there's only two of them. That makes finding limits in this context a lot more interesting. Generally, we will be able to determine the limits and their value, let's say algebraically, using good old-fashioned limit laws the way you know them and love them from Calc 1, or at least now their multivariable counterparts. But this particular scenario is very useful to show that limits don't exist, because all we have to do is come up with two paths of approach that yield different limit values for the function, and that means the limit cannot exist, because that means there cannot be one shared limit value among all the different paths of approach. So for limit problems in two dimensions, very often we're still only going to draw the xy plane, but that's because we're examining the domain. We're looking at what's going on in the domain. We will have some target point AB for our domain variables x and y, and we can consider all sorts of different paths of approach to that point. And see, I'm drawing them all straight. They don't have to be straight. They can actually be arced. So any way we want to come into that point in the xy plane is a legit path of approach. This path of approach business, again, is only used to show that limits do not exist, and in this next example, I'll show you how that plays out. We are going to look at the limit as x and y approach the origin of the function 4xy squared over x squared plus 3y to the fourth. This is not a quadric surface. This is not one that you can intuitively envision what it looks like. It's just some weirdo surface that floats around in three-dimensional space. Notice, however, that one thing we do know is that the value of this function is undefined at the origin. Because if we plug in 0 and 0, we're going to get 0 divided by 0, which is no good. But just like from Calc 1, the function not existing at the limit point has no bearing on whether the limit as we approach the limit point can exist or not. So we still have work to do, even though we can't plug in 0, 0. When thinking through limit problems, the first thing to do is worry about whether the limit might not exist. Because if the limit doesn't exist, then you're done. And so we need to figure out, is it possible for this limit to exist? And maybe we can show that it doesn't exist using the method of paths of approach that I just showed you some pictures about. So in our domain, in the xy plane, we are going to be approaching the origin. So we can approach from this way, we can approach from this way, we can approach from a whole bunch of ways. So let's think about these paths one at a time. So let's think about the approach to the origin on the path x equals 0. That is here. If we are on the line x equals 0, or on the path x equals 0, we're on the y-axis. So we are approaching the origin from above and below. If we're restricted to this single path, what we're doing is taking this limit that depends on two variables and reducing it to a single variable limit problem, because we're just going to set x to be 0. So if x is 0, the only variable that can wiggle is y, but we still want y to approach 0. And if we're on the path x equals 0, then it doesn't matter what y is, the rest of the function has zeros in place of x's. But notice, that's the limit as y approaches 0 of 0. Okay, so the function itself is reducing to the 0 function because this numerator is just flat, plain old 0 when we're on the path x equals 0. And this limit is 0. So as we are approaching the origin along the path x equals 0, the limit value that we get is 0. What if we come in from the left and the right? There we're on the path y equals 0. Well, look up here at this function and say, hey function, for the time being, we are only considering points on which y is 0. Well, this limit then collapses into a limit depending on x, but x is still going to 0. When we plug in y equals 0, we'll get 0 on the top. We'll have x squared plus 0 on the bottom. 0 divided by x squared plus 0 is just plain old 0. And then the limit as x approaches 0 of 0 is 0. So as we're approaching the origin from the left and the right, it sure looks like the function as a whole is approaching 0. So we've tried two paths of approach. We've gotten 0 on each path of approach, and that means we can celebrate and say, well, the limit of this whole function is then 0. Right? Wrong. Because we cannot show that a limit does exist by only showing two paths of approach happen to match in the limit value. We have to show it for all of them, and there's infinitely many, and we can't do that. So we have to hope that at some point we're going to stumble on a path of approach that will give us a different limit value. I'm going to try a different path of approach here. I'm going to come in along the path, oops, I'm going to write this in a different order. X equals y squared. Now, this is a weird guess, but when it's finished, you'll see why I picked that one. And as you see more and more examples, you will learn to develop other guesses of other paths that are kind of like this. Graphically, what this means is that we are coming into the origin along y equals the square root of x or along x equals y squared. So we are approaching the origin on an arced path. Now we go back to the function. We say, hey function, for the moment we are only considering points on the path where x and y squared are the same thing. So we're going to substitute y squared for x, which means that in the limit we're only interested now on the behavior of y, since x is now totally determined. If I'm on the path x equals y squared, I can say, hey function, x is going to be y squared for the foreseeable future, so let's just plug that in for x. And we get this, and look what's about to happen. This numerator is 4y to the fourth. This denominator is y to the fourth plus 3y to the fourth. Hey, that's 4y to the fourth. And oh my goodness, the entire function has just collapsed to 1 on that particular path. The limit as y approaches 0 of 1 is 1. And so that means that we have found a path of approach to the origin along which the limit value for this function happens to be 1 and not 0. And since now we have different paths of approach giving different limit values, this limit does not exist overall. That's pretty fun. Now here is a sermon about presentation of work. The work I just did was scratch work. It was my first draft. It was me tinkering with the limit problem in order to see what was going on. The work I just showed you on that messy page is not what I would actually hand in. Just like in any other subject, English or history or whatever it is, you don't just take out a piece of paper and start slopping stuff down on it and say, this is what I'm going to turn in no matter what. You organize your ideas, and then when you know what's going on, then you make a more polished presentation of the work. So here is what I actually might want to submit for the problem I just did. It's not just a bunch of testing and scratch work. It's got a beginning, a middle, and most importantly, an end. So I'm saying for this limit problem I needed to do, I checked the path x equals 0 and I developed a limit value of 0. And then on the path x equals y squared, I ran that limit and I got a 1. And my conclusion is that since we got two different limit values on two different paths of approach, the limit doesn't exist. Now, apart from the fact that my handwriting is a little bit messy, this is a much more suitable product for somebody else to read than the scratch work, the real-time thinking that was going on the previous page. When you're doing your own assembly of work, please make that distinction between scratch work and a nicely polished final product. Finally, here's a little visual help from Maple to let us really see what was going on with that limit calculation where we discovered different limit values as we approached the origin on different paths. The function was 4 times x times y squared over x squared plus 3y to the 4th. Maple decided to reverse the terms in the denominator when I typed it in, no big deal. Here's what that surface looks like. This is kind of a mess around the origin. It's a great big snarl, like if you had a tissue paper piece laying flat on a table, you pinched it in the middle with your thumb and index finger and kind of gave it a twist and lifted it up. That's maybe what this would look like, or what this describes. But you can see the x and y axes are indicated down here, and the z-axis is the vertical. The origin is kind of right there smack in the middle. So you can see, for example, as we approach the origin along x equals 0, it looks like we're heading for a z value of 0. See, there's z equals 0. So right there in the middle. Remember, this function is not defined at the origin 0, 0, but it's defined everywhere around it. And if we just if we're an ant and we're walking on this surface and we had to make a guess as to what z value we would end up at by the time we got to the origin, we might have said 0. Here that's even more pronounced on this little ridge right here. This is y equals 0, and if I'm a little ant walking along the surface and I'm approaching the origin on this path y equals 0, and I guess what z value am I going to hit when I get to the origin? Well, I'm at z equals 0 all along, and so my guess is going to be, well, yeah, I'll still be at z equals 0 once I get there. But look at this ridge up here. See that arc, that almost parabolic shape, such as x equals y squared? If we're an ant and we're walking towards the origin on this path up here, we're going to make a guess, because we're at z equals 1 all along, that by the time we get to the origin, xy equals 0, 0, we're still going to be at a z value of 1. And so that means that if we're approaching the origin from here, it looks like we're heading for 0. If we're approaching the origin on this path, it looks like we're heading for 1. You can even see a symmetric trough down here. This might be, that was like x equals negative y squared. That's an elevation of negative 1 down there, so there's maybe a different path yet where we could have discovered a limit value of negative 1 even. But there's conflicting limit values as we're approaching the origin from different paths, and that means that overall the limit does not exist.